lattice. This is what we call as a rectangular centered lattice. After I drew the figure, I realized that it's looking somewhat like hexagonal, but let's take this as a centered rectangular lattice. It means you have a rectangle here. These are only points, okay? And there is a point at the center of the rectangle. Initially, you may say that the environment of this point is different from this point, but that's not so, because this point can also be looked at the corner point of this rectangle. So, if you are sitting on this point, you can also imagine that you are at the corner of a rectangle or at the center of the rectangle, which goes with every point. So, environment of this point and this point is exactly identical. I cannot uniquely say that this point is the center of rectangle or at the corner of rectangle. This forms a Bravais lattice. This is one set of vectors. A is because it's two dimensional, so I have to have only two vectors. A is equal to ai and b is equal to a by 2 I plus b by 2 j, which is this vector. These two vectors, linear combination of this will generate the entire lattice. This you can verify yourself. I will give you the notes of all these things, later, so you can look at it and try to work it out. The another set of vectors which are possible is this, where you don't take this, but you take this vector. This is a little more symmetrical, but conventionally we prefer vector something like this, which is more symmetrically oriented. This will also equally well serve the purpose of primitive vectors for the same lattice. So, as I said, there are infinite possibilities. Now, let us go to three-dimensional lattices. I am going rather fast. If you take a simple cubic lattice, this is only one of the unit cell, but it's repeated infinitely in all the three directions. And remember, these lines have been drawn only for your convenience. What I mean is only points. The lines is only to show you that it's a cube, but otherwise the lines don't exist. It's only a set of points. Okay. The vectors that we normally choose is this: A is equal to ai, b is equal to aj, c is equal to ak. These are the primitive vectors for this particular simple cubic Bravais lattice. This is body-centered cubic. I am sure all of you know body-centered cubic lattice. Here you have an additional point also at the cube. Okay. Again, if you are sitting at this particular point, for every point, this can also be viewed as a point on the center of the cube or at the corner of the cube, depending upon how you look at it. So, the environment of this point is going to be identical to this point when I draw infinite such cells. Alright. In this case, normally this is what we choose as the vectors: a by 2 I plus j plus k, by 2 I minus j plus k, a by 2 I plus j minus k. Alright. I am not going ahead how this represents different points, but you can always view it. We have centered cubic lattice where you do at the center, but you have points at all the faces. Assume this room to be a cube. Okay, so you have points at all the corners and all the faces. There are 6 faces. Each of the 6 faces are centered. There is a point there, and this is what we choose as the primitive vectors. Remember, these primitive vectors cannot generate a BCC lattice. Similarly, BCC primitive vectors cannot generate FCC lattice. But the same FCC lattice can be generated by many such vectors. Alright, for example, if I would have taken A plus B and B and C, that would have also worked. Now there is a basis. So as I said, we need two things to represent a crystal structure: a lattice and a basis. Basis again is a very generic term. There are 3 places where we use the concept of basis. Okay, let's be clear about it. Basis is something that we systematically attach to each point of the Bravais lattice. This is done with 3 aims in mind. So, something is to be attached at these points. These are points, infinite points, set of infinite points. Okay, there are 3 reasons why I would like to attach something to these points. Convert a non-Bravais lattice to a Bravais lattice. I will show you the example. What is a non-Bravais lattice? What is a Bravais lattice? I will give you an example. Alright. So, convert a non-Bravais lattice to a Bravais lattice. Second, convert a Bravais lattice to a simpler Bravais lattice. That also I will give you an example. Third, which is most important for us, to put an atom or a set of atoms or ions identically at each point of the Bravais lattice to generate an ideal crystal. An ideal crystal. An ideal crystal is always infinite. It does not have any defect. Such type of crystal cannot be produced in laboratory, because whatever you do, you are always going to produce finite crystal. It's impossible to make it defect free. There are always going to be defects. All right. So this is the utility of the concept of basis. Suppose you have set of points like this, infinitely varying in all the three directions, this direction, this direction, this direction, this direction, this, all the six directions, exactly same thing. You can very easily see that this is not a Bravais lattice, because if you are sitting on this point, you are seeing a point at this distance, let us say x, along the diagonal. But if you are sitting on this point, you don't see a point exactly identically located. It's not, there is no point at a distance of x in this particular direction. If you have moved from this point to this point, you are definitely sure that you are not at the original point. So this set of points does not form a Bravais lattice. But if I couple these 2 points and treat this as one point, that will form a Bravais lattice, and I will say one Bravais lattice with 2 points. This will generate a non-Bravais lattice. So there are many non-Bravais lattices which can be thought of as a Bravais lattice by using the concept of basis. One of the very important example is diamond, which I will just now describe. Diamond, if you just replace all the carbon atoms by points, it does not form a Bravais lattice. So you require 2 points basis to generate a diamond structure or diamond lattice, which is a non-Bravais lattice. Sorry. Alright, is this point clear? There is another example of what we call as a honeycomb structure. Different hexagons. All these black points, they do not form a Bravais lattice, because if, for example, you are at this point, at a distance of a, you see another point here. But if you are on this particular point, you do not see a point at distance of a here. So the environment of this point is different from the environment of this point. Therefore, these set of points do not form a Bravais lattice. But if you couple these 2 points into one point, this forms into what we call as a simple hexagonal Bravais lattice. Okay? This is the Bravais lattice, because here if you are going at a distance of a, you do see a point here. Or in other words, instead of honeycomb, if I would have put one more point additionally here, this would have formed a Bravais lattice. But as such, it does not form a Bravais lattice. Now by taking 2 point basis, I have converted a non-Bravais lattice into a Bravais lattice. Then conversion into simpler lattice, this is very generally done in the case of X-ray diffraction. A body-centered cubic lattice is not looked as a body-centered cubic because its primitive vectors are very complicated. Okay, we rather treat this as a simple cubic lattice, which is easier to draw, easier to understand, and treat a body-centered cubic lattice as 2 point basis. Okay, though BCC lattice in its own self is a Bravais lattice, but still we decide to treat this as a simple cubic lattice with 2 points basis. So a body-centered cubic lattice can also be looked as a Bravais lattice, a simple cubic lattice with 2 points basis. A BCC lattice can be thought as a simple cubic lattice with 2 point basis, with 1 point at 0, 0, 0, means you start at a point, put one particular point at the origin, another point at a by 2 I plus a by 2 j plus a by 2 k, which is the body center. So you have this room, okay, you take this point, you put 1 point here, 1 point at body center. Similarly, you go to that particular point, you take 1 point there and put 1 point at the body center. You take 1 point, you put 1 point at the body center. Alright, you will generate a BCC lattice, which also is a Bravais lattice. But we prefer to call it many times, especially in X-ray diffraction. X-ray diffraction indexing always is done assuming a simple cubic Bravais lattice with 2 points basis. Alright. FCC can be considered as a simple cubic lattice with 4 atoms basis. These are the atoms. These are the placing of the atoms. You are starting looking, look at this face center, look at this face center, look at this face center. Then take another point, put 1 point at that face center, that face center, that face center. You will be able to center all the faces. It's always, because or not very easy to draw a 3-dimensional figure. I have found it much easier that the room in which you are sitting, assume this to be a cube, and then look at the walls and try to see. So you have all the faces centered. You start from here, This face is centered, this face is centered, this face is centered, and one point here. Right? Then if you go to this particular point, this face will get centered. Then that face will get centered, the other face will get centered. You will find everywhere all the faces will get centered. So FCC lattice, which in its own self is a Bravais lattice, can be thought of as a simple lattice with 4 point spaces. All right. If you have difficulty, please ask me a question, because we are going now a little bit more. Normally, I would have spent 2-3 lectures only on this particular, but I'm going a little faster. Now, this is us. At each point of the Bravais lattice, one can put an atom or set of atoms in identical way to generate an ideal crystal structure. Sometimes the students are confused because we always show crystal structure with point. They think that's what is the atom is, and there is a big stick which is joining these two atoms. That's not a correct picture. Okay, a more correct picture is that you assume that there is a big hard sphere there, another hard sphere which can be treated as an atom, and they are joining together. So what we are showing is only lattice points. It does not mean that atom is that tiny and located at this and there is a rod which is joining them. This is a misconception which a lot of people have looking at all the figures which are given in the textbook. So this is what I call as a hard model. In this model, as an approximation, we treat an atom or ion as a hard sphere, something like steel ball. In the hard sphere model, we assume that these hard spheres touch their nearest neighbor to form the structure. What we show the structure are replaced by spheres. That's what we are doing. In fact, hard sphere is also not a correct model because otherwise lattice will not vibrate. Okay, so in principle, they have to be elastic spheres. Then it cannot be even elastic spheres, otherwise there will be no thermal expansion. And then you have to take anisotropic things, anharmonic interaction. So things are very complicated. As that's what I mentioned as a first approximation. As an approximation, we can treat them as hard sphere. And for crystallography person, hard sphere model is the model. We get a lot of idea about the crystal structure only from hard sphere model. Now I will come to the diamond structure. This is little complicated, so let's go slowly and try to understand it. Diamond structure is a FCC lattice with 2 atom spaces. It means, as I just now mentioned, if you replace all the carbon atoms by points, this will not form a Bravais lattice. How? I will show it later. Okay? It means you require essentially 2 points, like in the case of honeycomb structure or 2 other points. Okay? Another picture where it was not forming a Bravais lattice. Diamond also does not form a Bravais lattice. So, in solid state physics language, what I will treat that this as a face centered cubic lattice, where at each point you are putting 2 atoms of carbon. Okay? Let us first understand diamond non-Bravais lattice. So I am just replacing all the carbon atoms and just showing them by points. Only non-Bravais lattice I am showing. How to represent by lattice and basis, I will discuss later. So let us start with a face-centered cubic unit cell. Here I will go a little slower. Please do raise your queries because I know these are not very simple. Any questions? Anyone? Okay. So this is a unit cell of a face-centered cubic lattice. You agree? Okay. Not all the faces are clearly visible because the ones which are behind I am not able to draw. Okay. If you have difficulty, assume this room. Alright. So whatever are the face shown, this face is centered, this face is centered, this face is centered. Similarly, there will be a face here which is hidden, that will be centered, another face which is here, that will be centered like that. Okay. Let's assume that this is the lattice constant, which we generally call as a cube edge, is A. What I have done, this cube I had divided into 8 cubes, each of length A by 2. Okay. You will get 1, 2, 3, 4. These you can see here, 1, 2, 3, 4, 4 behind it. Alright. You will have 8 smaller cubes of dimension or edge A by 2. divide into 8 smaller cubes. Alternate of them you center. Suppose we take this tiny cube, center it. It means I put another carbon atom at the center of this cube. This tiny cube, not the big cube, which has a dimension of a by 2. I put one atom here, but the next one I don't put. In any direction you move. You go here, then you put. Then you go in this direction, you don't put. So keep on taking alternate of them. Is it clear? This room divided into 8 tinier rooms. If this is centered, that is not centered. That will be centered. This will not be centered. This will be centered. That will not be centered. Alternate of these tiny cubes will be centered. This is what is diamond structure, diamond lattice. Is it clear? Again repeat. Big cube divided into 8 smaller cubes. Alternate of these cubes are being centered. Alternate of small cubes are centered with additional points giving diamond non-Bravais lattice. So let us show that this is not a Bravais lattice. What cut this to 2 rooms. Okay, one dimension will be A. Okay, this dimension will be root 2A. A root 2A. Okay, if I join from this point to that point, that will be root 3A. So this distance is root 3A. All right. This corner was centered. This was centered. This was centered. Because we are going in the direction. You remember, it's a 3-dimensional picture. I am looking at this particular direction, so it's not very clearly visible. You have to imagine it. Okay, if I am doing like this, okay, let's put how, which is the best way to put. That is centered. Then this will not be centered. This will be centered. So that these 2 centers are coming here. These are 2 uncentered. Remember, I am edging it like this. That tiny cube was centered. This was not centered. This was centered. In this direction, there will be one room below here, 1 point below here, 1 point below here. These are the 2 points. Okay, but above this, because this centered, so above this has to be non-centered. So there is no point here. Above this has to be non-centered. So there is no point here. If you just cut into half, this is the picture you will get. Now it's clear that if you are at this particular point, at a distance of this root 3A by 4, you see a point. But if you are sitting at this particular point, at root 3A by 4, there is no point. This point and this point are not identically located. Clear? This does not form a Bravais lattice. Clear? Any doubt about this particular thing? All right? This is what I have said. At each point of the lattice, we put a carbon atom, we get a diamond structure in this particular lattice. It can be expressed as 2 interpenetrating FCC lattices, one displaced with respect to each other by distance of 1/4 of the body diagonal. Huge sentence, big sentence. Let's try to understand the meaning of it. Suppose we have 2 identically face-centered cubic lattice identically placed on the top of each other. Okay? Now you take one particular lattice and move along the body diagonal like this, 1/4 the distance of the body diagonal. So this atom which was there now will become corner of this particular room, or that small tiny room. Okay? So this is the way of expressing a diamond structure. But I am more interested in the language of lattice and basis. Diamond is a FCC lattice with 2 atoms basis. At each point, you put one carbon atom at the origin, another point at A by 4I plus J plus K. Had it been A by 2I plus J plus K, it would have become BCC. Alright? It's A by 4. So you take one particular point, go A by 4, you put point here. Okay. Similarly, that particular point A by 4, it will put that particular point. Take every point of the face centered cubic, go and put one point there and another point at a distance of 1/4 of the body diagonal. You will generate the diamond structure. Is it all right? Any questions about this thing? I am going to go to more complicated structures. So if you have any difficulty, let me tell. Let us tell. It requires a little bit of imagination. I will not be surprised if you don't understand. You still have time. You can think over it. Okay. I am here tomorrow. I am here day after tomorrow. You can contact me. All right. The two structures that I am going to talk, which are useful structure, one is perovskite structure, another is spinel. Perovskite is comparatively simpler structure in comparison to spinel structure. But there are lot of useful materials which are specializing in a perovskite or a modified form of perovskite structure, which includes, materials which are used for spintronics, CMR, high temperature superconductivity, a very, very large section of materials specialize in perovskite or its modified structure. Let us look at an ideal perovskite structure. What is meant by ideal perovskite structure? I will tell you. I will explain to you what is meant by ideal perovskite structure. Okay, it has 3 different type of ions. One is oxygen. There are other two which we call, let's call A and B. All right. And the structure is of the type ABO3. It means one molecule will have 3 oxygen atoms, 1 atom of A, 1 atom of B. Agreed? All right. ABO3, simple cubic unit cell. This is described as follows. Corners of the cube. How many corners are there? 8 corners. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 corners. Ion A is sitting on A. 8 such corners. Okay. But remember, each corner is being shared by 8 similar cubes. If you take this particular corner, there is going to be a room like this, for which also this is corner. There is another room by its side, for which also it is corner. There is a room behind it, for which also it is corner. There is a room at that diagonal thing, for which also it is corner. And there are 4 such identical rooms below it. Okay. So, there are 8 cubes for which this particular point is corner. So, effectively, if I take on the average, there is only one point, because there are 8 such corners, each of one contribute 1/8. So, there is only one atom per unit cell. Okay. And here is ABOE, so there is only one atom, A. All right. Ion B is at the body center. So, there is one atom at the body center. I am not describing lattice at the moment, I am just describing the overall structure. There is one particular atom at the center. And because this is only at the center, it is not being shared by any other cube. Okay. There is another room that will have its own center. In this room, there is only one center, and that is being occupied by B. So, therefore, there is also only one atom of B or one ion. Okay. I may be confused sometimes saying atom or ion, but you understand that is the same thing what I mean. All right. Okay. So, there is going to be only one B ion per this unit cell. So, there is only one ion. While oxygens are on the face centers. How many faces are there in this room? 6. 1, 2, 3, 4, 5, 6. All right. Each of them has an oxygen at their face center. This face is common for how many faces? For how many cubes? 2. But this is a common face only for this room and for that room. For no other room. So effectively the 6, all right, only half of them are included in this room. So there are overall 3 oxygen ions within this room, ABO3. All right, it satisfies this condition VO3 by this structure. This is how the atoms are distributed in perovskite structure. Agreed? Any doubt? This is what I have tried to draw a rough figure. See, let me admit all these figures I have drawn myself, and I am not very good drawing person. Yeah, okay, and without using any very great software, so just using Word, I have tried to. So you may find, they are not exactly to the size the way I wanted, but please excuse me for that. So I have not taken from any book or anything. This is all drawn by me. So you can see that corner A, O, and this one atom. Agreed? Now come to the language of lattice and basis. It is a simple cubic lattice with 5 ions basis. Diamond was only 2. Here we have 5 ions. Okay. This will generate the entire perovskite structure. Simple cubic lattice with 5 ions basis. Let's try to look at the nearest neighbors, because for many of the properties, what our environment is very, very crucial. In magnetic materials, when we are talking of the exchange phenomena, it depends on what are the neighbors, how they are interacting. Because the neighboring atoms or neighboring ions have the maximum influence on a particular atom or ion. So how many of them are there, how they are placed, how they are located is very, very important. All right. So let us try to look at the different neighbors to different ions. Okay. I'll explain to you how I am getting. Okay. First one is A has 12 nearest neighbors of O at a distance of A by root 2. This is A. This is the nearest. This is A by root 2. In phase center, this and this point is the nearest point. All right, you are in this particular room, you have here and you have another. Of course, at this phase center, you do not have A ion, but you have red ion which is O. So its neighbors are O, oxygen ions. Is it clear? Its neighbors are oxygen and its neighbors are not A. Nearest neighbors I am talking. Agree? How many of them are there? You take one point this, okay, this is the nearest neighbor. This is one face, another face, below face, 4 such neighbors. Then 4 such neighbors in this particular direction. One here, one here, one here, another. 4 in this particular direction. There are 3 different type of planes which are coming here like this and like this. There will be 12 nearest neighbors. Can you visualize it? If you take one particular point, in fact, this happens even in FCC lattice. Okay, if you take an FCC lattice, here if you take this particular point, see these are supposed to be close packed, it has to have 12 nearest neighbors. Okay, you take this particular point, this point at this particular phase center is the nearest neighbor, which is at A by root 2. This distance is A, which is larger. How many such nearest neighbors will be there? You take this particular direction. 1 wall, 2 wall, 3rd wall, 4th wall. Their centers will all be at a distance of A by root 2. Then through this atom, this wall is also passing. Okay, so there is one here, one below here, one that particular direction, one in that particular direction. 4 plus 4, 8. Then in this direction also there is a wall passing. So from here to this phase center 1, here to that phase center 2, here to that, here to that phase center 4. There will be 12 nearest neighbors. Okay? At a distance of a by root 2. Okay? Just look at E. E. Just look at E. E is this 3. This is by 2, which is 5. Here, 3, 6. Actually, it can be seen very easily from this picture itself. There are 6 neighbors. Agreed? We have 6 nearest neighbors O at a distance of a by 2. Fine. What about O? O is this. Nearest is this, a by 2. This is larger, it's 0.75, it's 0.87. This is, for this oxygen, nearest is this a by 2. Okay, it has only 1 and 2. This oxygen atom has 1 and another one here. Another distance of a by 2, here there is no ion. Can you see? Look at this oxygen ion. Here at a by 2, there is one green. In the neighboring room, there will be another green here. It will have only 2 green neighbors. If you go a by 2 distance this side, here there is no point. If you go a by 2 here, there is no point. If you are going a by 2 in this particular direction, there is no point. Alright? If I am looking at this phase center, there is only one point at this center and one in the next center. These are 2 its nearest neighbor. But if I go a by 2 distance here, here there is no point. If I go a by 2 distance here, there is no point. It has only 2 nearest neighbors. Is it all right? Any doubt, any confusion? O has 2 nearest neighbors of B at a distance of a by 2. Now let's imagine a funny thing. Hard sphere model. Everything is touching every nearest neighbors. All nearest neighbors are touching each other. So let's assume, let me put in a proper question form. What should be the ratio of A, B and O ions so that it's the most stable perovskite structure? What is meant by perovskite structures being stable? That all the closed atoms are touching each other. Then it's compact structure. If one of the side is becoming bigger and there is one atom here, there will be gap. Okay? Because of this, it becomes easier to distort it. Okay? Ideally speaking, you will never have a perfect structure because the ions, their radii are not under your control. Alright? But let's try to evaluate it. Okay? The radii of ions are Ra, Rb and Ro. Let's assume that all ions touch their nearest neighbor in the most stable configuration. B is touching O, that we have seen already. If this is touching this, then the radius of B plus radius of A should be equal to 0.5A. These two are touching, one is bigger, another is smaller. Okay? But the sum of the radii, if they are touching, should be A by 2. Alright? Then Ra and Ro. This is R, this is A and this is O. Ra and O, so this is O, this is Ra and Ro. If this is also touching this, then radius of A plus radius of O should be equal to A by root 2. Alright? So Ra plus Ro is equal to A by root 2. This is under the stable configuration. And remember, Ro common, then A by 2 has to be larger than Rb. Alright? Then only these equations are satisfied. Whether they are satisfied in nature or not, that's a different question. I am looking at the moment at the ideal structure, or rather most stable structure. Not ideal is not a good word. Most stable structure. Then generally, because oxygen ions are negatively charged ions, they are generally biggest in size. Because the last additional electron which has come, which is completely loosely bound, make the size bigger. Okay? Positive ions, because they have lost one electron, their size becomes smaller. Generally, negative ions have larger radii. Alright? Now, let's assume that these oxygen ions are also touching each other. Ions are also touching each other. Set. Then you must have a by 2 square plus a by 2 square is equal to 2 times r. The distance between these two. Distance between these two oxygen ions is a by 2 square plus a by 2 square. Under root, of course. Alright? First go from a by 2 distance, let's say a by 2. From here you must come to a by 2 distance way, a by 2 distance this away. So this distance will be a by 2 square plus a by 2 square under root. And if they are also touching, and these are involving only oxygen ions, so that must be equal to 2RO. Expression in terms of lattice constant. And you just solve these equations, you get this is the ratio. R naught to RA to RB should be 1:1 is to 0.41. If these are the ratio, then you will be able to form the most stable perovskite structure. Agreed? But in general, it will not happen. Okay? Something will go loose, something will become larger, something will be smaller. And therefore, sometimes the structure will continue to remain in the site, sometimes it will start distorting heavily. And that's what happens in perovskite, because there are large number of ABO3 type of compounds, which are the Slazine perovskite structure. You get a range of structures. Alright? We define what we call as a tolerance factor. You pick up any textbook on solid state physics, you will get all these values of atomic radii. Okay? If you find Ra is the radius of A ion, radius of O ion, you have to take ionic radii. Alright? This is atom radii, because atomic radii will be different. This divided by this. This is what is called tolerance factor. For most stable structure, this should be equal to 1. This is from the equation. Alright, you have read these two equations. Alright, you will get 1. This factor is 1 for idealized structure. Now, if you are taking a realistic value of Ra, Rb and Ro, if this is lying somewhere close to 1.9, 0.85, 1.5, then this will retain still the perovskite structure. Otherwise, it will start distorting. And distortion can be of multiple type. And that's what makes perovskite material very complicated and very interesting. Depending on what type of ionic radii you are using, the structure may become quite different, may even lose cubic symmetry sometimes. Normally, if T is around 1, the structure is stable as cubic. If T is quite different from 1, various other structures different from cubic are seen. I would just like to tell a little bit about the environment of each atom, which makes, yes. Atomic, can you speak in the mic, please? Atomic form factor. No, packing fraction is very different. No, I'll explain to you. Packing fraction, they are related in a sense. Packing fraction essentially means how much of the percentage, you assume hard sphere. You have total volume available. Out of that total volume, how much, what fraction of that particular volume is occupied by atoms? That is what is packing fraction. That's correct. See, packing fraction in principle. See, packing fraction, if more, it depends on density. That's a different thing. But here I am not talking of density. I am talking of relative radii. All right. Of course, packing fraction will become different if the radii becomes different. Or let me put it like that. No, I'll reform your question. If I have this particular tolerance factor as 1, I will get maximum packing fraction.
Yeah, that is what.
Okay, so I have rephrased your question. Okay, if tolerance factor is 1, then packing fraction will be maximum. If tolerance factor is less than 1 or greater than 1, then packing fraction will be different or will be smaller than this. Because there will be some spaces which will be left behind. One particular side may expand to accommodate a bigger ion. Okay, in that case, some of the space may get wasted. Have I answered your question? So let's look at the environment of these A and B ions, because this is something. Yeah, you have some question. Look at this environment, which is, I think, very interesting aspect, because this is also something which is very, very commonly used. As we have said that B ions are surrounded by 6 oxygen ions. This is what we call as octahedral arrangement. I will show you that octahedral arrangement in the next picture. The A ions are surrounded by 12 O ions. This is what is called cuboctahedral. The site, I'm sorry, I don't even know how to pronounce it properly. Its site, it's a very complicated site. It contains of 8 triangles and 6 faces. I mean, it was impossible for me to draw that particular figure. So I would suggest that you look at any book or do Google search of this particular site. They will show a very nice, beautiful picture of this particular thing. Okay, but let's look at the octahedral site, which is actually interesting. Right? This is my O. Sorry, this is my B. Okay, you have 6 ions, face centers. Can you see octahedral? 1, 1, 1, 1. This is the octahedral site. 6 ions surrounding it. It will be covered by 8 faces. This is the octahedral site. So the B ions find themselves into octahedral environment of oxygen ions. So once you start looking into this particular property of this particular ion, you should realize that this is under octahedral arrangement of ions. On the other hand, if you are looking at A, it is that complicated type of structure which it is surrounded by oxygen atoms, by 12 oxygen neighbors, which are in a very complicated fashion. Okay. Do you agree? This is just this picture I had tried to draw partially, but I think it's not very. Let's forget about it. Any questions regarding this structure now? Because I will go to one step further, which is spinel structure, which is still more complex. How many of you have heard about spinel structure? Quite a few, quite a few. Some of you have used spinel structure, or you are working a material which has a spinel structure. Okay, let me just take a little bit of time to describe it. Let me tell you that this structure I am describing in a fashion which is reasonably different from the way it's described in. All right. So exact similar type of discussion, I will say how it is described in textbook. Also to you. And the reason I have preferred to describe it in my way. See, as I said, solid state physics people always want to talk in terms of a lattice and a basis. And I, being solid state physicist, I prefer to describe it in that way. All right. Metallurgist, material scientist, okay, they want to describe in their own fashion, which makes them easy to understand their structure. So they define this structure in a slightly different fashion. So most of the picture that you will see in textbook have been drawn in a slightly different fashion than the way I have drawn it. Okay, and being 3 dimensional, it's not very easy to see the equivalence, but I will try my best to explain to you. It has a formula of type AB2O4. All right. However, its unit cell does not contain just one atom, unlike perovskite. Okay, perovskite has one formula unit, one per unit cell. Here, its unit cell contains 8 such molecules. All right. So, one unit cell is a fairly complex structure. 8 such molecules of this will be put. Has a AB4, has a 10 cubic unit cell. That's all I will explain. And contains 8 formula unit compound. Oxygen ions form the basic unit cell, which has 2 tetrahedral and octahedral sides. This structure is best described if we divide the unit cell into 8 octants of the lattice constant. Now let's try to understand. We are now going to in diamond structure, we started with FCC and cut into 4 smaller cubes. Now I am going to take this FCC lattice itself and put 8 such FCC lattice and putting into a bigger unit cell. Going to other direction, its unit cell, if I divide into 8 different parts, the way I have divided diamond, each unit cell will be full face-centered cubic unit cell. Unlike diamond once I divided into 1 8, it did not show face-centered. It showed only a tetragonal symmetry, 4 points. All right, but here it's much bigger. Or in the other hand, if you have this face-centered cubic unit cell, you assume 8 such face-centered cubic, 1, 2, 3, 4, 4 on the above. That will form the unit cell. Okay, its unit cell contains 8 FCC unit cells. And it has 2 types of vacancies, tetrahedral and octahedral. Let's be careful and draw slowly. So I have started with the unit cell of spinel, which has a lattice constant of A by 2. I divided this into 8, and unlike diamond, here each of these 8 lattice constant A by 2 are full unit cell of FCC lattice. Agree? This is the FCC of lattice constant A by 2. Consider one such divided into 8 smaller cubes. Now I have gone to second level. Then I will get like diamond type of thing. They are not FCC. Like diamond, this will have tetragonal type of thing. You see tetrahedral coordination with point A by 4. See, this tetrahedral symmetry was also seen in diamond. All right. So this is A by 2. And now this is a full FCC unit cell. This full unit cell has been divided into 8 smaller unit cells of A by 4. Within this I was putting in diamond tetrahedral coordination. 1, 2, 3, 4. It's a tetrahedral coordination. 4 faces. Can you see tetrahedral coordination? Diamond also had a tetrahedral coordination. But now I am not starting with FCC lattice, I am starting with the FCC lattice which is twice of that size. I am starting with A. First I divided into 4 A by 2. Now I am dividing further of A by 4. And now I see in this that each of these sides has a tetrahedral coordination. Can you tell me in a full unit cell of spinel, how many such tetrahedral sites? Difficult question. Who said 60? 64, yes. Who said, you said 64? Who said 64? Raise your hand, you've given a correct answer. Who said 64? Yeah, 64, really 64. There are 8 such, no? All these are sites. Alright? All of these are tetrahedral coordinated. You could have put iron here, 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 here. Whether they are occupied or not, that's a different question. But site is there. Okay, it may not be occupied. But if instead of this, I would have chosen my atom to put here, it still be tetrahedrally coordinated. Okay, so there are 8 available in a cube of A by 2, and there are 8 such cubes. 8 into 8, 64 sides. So in a spinel, you have 64 tetrahedral sites. Obviously, not all of them are going to be occupied. You have only 8 formula units. You have only 8 formula units. Alright? But is it clear? Can you see tetrahedral site? I think you must have seen earlier also diamond structure, which they say tetrahedrally coordinated. So it's exactly the same thing that I'm talking, except it's a big larger scale. Should I go ahead? All of you are satisfied? This is the tetrahedral site. And each of them have a similar environment. They may be rotated, but they'll have all these 64 sites. Many such sites are there in spinel set. There are 8 small cubes of edge A by 4. Within each, there is one octahedral site. Hence, there are 8 sites within FCC unit cell of A by 2. We therefore have 8 into 8, 64 tetrahedral sites in spinel unit cell of edge A. Fine. Now let's calculate the size of this particular site. I will not do it because I think I should not miss on the time. 4 o'clock is my ending lecture. Okay, so I think I will not do it. I'm just, anyway, these slides I will make you available. Okay, so you can look at the size. Again, you have to see which atoms are touching each other and things like that. All these things. You get, if you take R0, typically oxygen and radius, which is given in a table, is of the order of 1.4 angstrom. Then the lattice constant of spinel turns out to be 7.9 angstrom. And radius of A ion will be the A site. Maximum you can accommodate is 0.32 angstrom. It's very small. Most of the ions will be bigger than this size, and therefore they will not touch each other. These touching, etc., will not work. Fine? Site is bigger actually. Small in comparison to the constant of most of the magnetic spells are 8.4 instead of 7.9 that I have calculated using oxygen ion ratio. In order to adjust bigger ions, there are some adjustments done which are defined in terms of parameter called U parameter and become different. Okay, I will not discuss about U parameter because that would have made things much more complicated. See, like you have parameter T parameter for perovskite, also here you have a U parameter for spinel. Okay, and if you want to see, this is the ideal book, Smith and Will. Very, very old textbook which describes these things in great detail about these U factors. Now let's look at the tetrahedral site. Take 1 octant of spinel unit cell, which is the FCC unit cell. Take a point at the body center of this unit cell, which is unoccupied. Imagine a point there. Octahedral coordinate can be clearly seen. Yes. This is A by 2 size. which is 1/8 of the original spinel unit cell. All right. I have taken 1/8 and that 1/8 of that cell, and that is still FCC cell. That's what we have said. So you can see FCC, all black ions are all FCC. I put an ion here at the center of this thing. All right. There is no ion otherwise in the lattice, in the unit cell. Okay. But I am putting in this particular thing. Okay. If I put an ion here, then you can see it's exactly like the one picture I have shown for perovskite. One on the top, this yellow line, one here, one here, one here, one here, one here. This is octahedral coordination. All right. Now let's calculate the number of octahedral sites. Any point located in between oxygen ions which are distance a by 2 apart. Essentially it means that if you have an oxygen ion here, in between there is going to be a B site. So whatever is the number of sites of oxygen, same should be the number of the lattice. So there are 4 sites on the average, and here therefore 32 such sites will be there in a unit cell. So there are 32 octahedral sites and 64 A sites, which are totally available to you in a structure of oxygen that has been formed. Site of the size is slightly bigger, 0.58 angstrom. Now I have to distribute these ions into these sites. How it is distributed? In normal spinel, there are various types of spinel structure. What we call is a normal spinel. The octahedral site is occupied by divalent atom and trivalent and and divalent ions occupy A site. Inverse, it's the other way. Half of divalent occupy. I think you understand it better. Because in my flow, I can make mistake. In a normal spinel, 8 of the 64 H sites are occupied by divalent ions, because you have A, B, O4. So A has to go to tetrahedral site, and there are 64 sites. So only 8 is going to be occupied by divalent ions, while 16 of 32 B sites are occupied by trivalent. Because A, B, 2O4, and there are 8 in each, 8 formula units of each, it means you require space for 8A, 16B. Alright. So, in inverse spinel, half of the trivalent ions occupy A site, while the balance half divalent ions occupy B site. Balance half and divalent ions occupy B site. The preference of an ion to go on multiple factors besides size. Size is only one of the criteria. There are many other criteria. In fact, which ion goes to which site, is a very, very complicated thing. There are so many factors which decide which ion goes to which site. See, normally a 3+ ion should have a smaller size because 3 of its ions have been stripped off. But in that case, every spinel should be inverse spinel. But it doesn't happen. So that's not the only criteria. There are other criteria. You look at this book, he has given varieties of things. Now, this is what I am calling as a block unit cell. The unit cell had a dimension of A. I have divided into 8 smaller units. Each one of them are FCC. You will find one corner and the neighboring coin. They are differing in structure somewhat. Let's call this as P and this we call as Q. Then above it will be QP. Then below here will be PQ. I am not sure whether you understood this. See, if I am taking only one unit cell, 1/8 of this particular thing, and I take its neighbor. I have taken a unit cell of dimension A divided into 8. Alright, I take one of these 8, if I take one and its neighbors, the distribution of ions are not similar. Is it clear? So, let's assume this base, there is one particular smaller cube here, there is one particular smaller cube there. So, whatever is the distribution of ions here is different from distribution of ions there. But what is the distribution of ions there will be similar to the distribution of ions above this. Alright, have you understood it? And what is the distribution of this will be above that particular thing. So, P represents a set of distributions octants and Q represents its neighbor octant. P and Q distributions are different. To go to P, it will have a distribution similar to Q, this Q. And if you go above Q or Q, then its distribution will be similar to this. It essentially means that this can be treated as FCC unit cell with a base P plus Q. Because P and Q are not identical, otherwise one would have been enough. Understood? All the P octants have same positioning of cations. Similarly, all the Q octants have the same positioning. However, between P and Q they are not identical. We can call this as FCC lattice with P plus Q combined together as well. What we have shown is a block unit in a conventional cell. I mean, if I take a simple cubic unit cell and treat this as a conventional unit cell, then this entire 8 thing forms the unit cell. Even if you don't understand the last sentence, it's not important. Can I go ahead? Look how tetrahedral. See, I'll do 3 steps. First, let us see how tetrahedral sites, 8 sites of 64 are to be taken. So, distribution of octahedral sites. Then, out of 32, how 16 octahedral sites have to be taken. Then, how these distribution of A and B sites are related to each other. Then, I have defined the unit cell completely. Then, I will talk about the positioning and I will talk about super exchange interaction. Is it okay? Clear? The sites, because I have taken now 2 octants, so there are 16, 2 are filled only. Okay, there are others, so that will make it 8. Lattice constant A, one displaced with respect to the other along body diagonal by a distance of root 3a by 4. We agree that this language I used in diamond structure. It means if you forget about everything, just look at the positioning of tetrahedral sites, filled tetrahedral sites. They would form a diamond structure of lattice constant A. If nothing else would have been there. This is just a way of viewing it. Everything else is there. I cannot forget about it, but it's just a way of viewing it. It's all right. To position it, it's a very interesting problem. Hence, the cations on A side form a diamond structure with lattice constant A. This is what I have just now mentioned. So, same language, exactly same language I have used for diamond structure. 2 interpenetrating FCC lattice, one displaced, 1/4 of the body diagonal. Often the spinel structure is shown by taking unit cell with A. This is what most of the textbook will give you. They will take unit cell of A and show other sites. They find it much more convenient. I am taking unit cell of oxygen ions because that translates better into lattice and basis. So that's the way I am differing from most of the textbooks which are in this particular subject. That's what I saw. Often the spinel structure is shown by taking unit cell with A site ions. This makes it somewhat simpler. Let us look at the position terms. Now I am going my way. Let's take one particular arbitrary A site filled. All right, let me just show the picture. This is A. This I have taken P plus Q. All right. That positioning of cations here in this block is different. I have chosen one block here. I have put one ion here. I have filled one of the tetrahedral site because out of its own it's going to form a diamond structure of lattice constant A. It means the next ion in the same line filled will be distance A away because the distance between them has to be A. Okay, you are getting too much tired, you tell me, no, we can stop at any time, continue that. Okay. Now this is dimension of A by 4, so dimension of A by 4. So I have to leave 3 blank and after that the 4th one will get filled. Alright. But in order to make it diamond, I have to put another ion at a distance of A by 4 I plus J plus K. So if I have started here, I have to put in this particular unit cell one more ion. Here, then I have to put back there. This is filled. Then after 4 unit cell, there will be another tetrahedral site will be filled. But that doesn't form diamond. For diamond, I must have another atom at a distance of A by 4 I plus J plus K. So if I move along body diagonal, I will fill this particular ion. This particular tetrahedral site. So this particular tetrahedral site is filled. Along this direction also, once I have filled, it has to go a distance of A for filling other. So you see, sites is filled in this particular thing. And they are all in Q. Is it all right? Making sense? Once one of the A site is occupied, the next one to be occupied in X, Y or Z direction would be only after a distance of A. The separation between 2 neighboring cubes, the center of which are the A sites is A by 4. Hence, after occupancy of A site, next 3 will not be occupied in either X, Y or Z directions, only 4th will be occupied. After filling these sites, a site located at a position vector of A by 4I plus A by 4G plus A by 4K shall be filled, which is 1/4 the body diagonal you go, lattice constant this direction, that direction, this direction. This is what I have shown here. Yeah. Beg your pardon?
So, experimentally, we can have control on that.
That's a very good question. These sites are governed by at least a spinel structure. I have not found that there is a control where you can, because otherwise the crystal structure itself gets distorted, the symmetry gets distorted. And I have not seen any evidence of spinel structure getting distorted this way. However, the occupancy of the ions, that can be sort of, depending upon, in fact, some of the results that we are going to show in one of the conference talks are where the occupancy of these sites we could control to some extent. So which of the ion is going to occupy which site, that somewhat you can control, somewhat, okay, but not really changing that, instead of this particular site, some other site, but then the entire crystal structure gets distorted. Is it all right? Any other question?
Sir, if we are cooling down a liquid and we start with specific like AbO3 we had, so do we always get a unique crystal structure every time when we cool down?
If you cool down uniquely by a particular process, you will always get the same structure. You should get by the same structure.
So we always get.
You should always get the same structure.
Okay.
But it's possible to alter the structure by, let's say, quenching. Because see, what happens, the stable structure at a particular temperature may be different. A higher temperature may be different from, let's say, lower temperature. Then it's possible that if you are suddenly cooled, the ions could not have time to move to their preferential structure at that particular temperature. And therefore, you could change the magnetic properties.
Like we are lowering the free energy when we cool down. So there might be some kind of degeneracy and we can get a different structure which has same positional energy, because this is, what I am imagining is these are like charged spheres. Charged spheres, hard sphere we are calling it, and they are charged, right? So
Yeah, they are charged, yes, of course. Yeah.
So we are trying to lower the potential energy. Is it like that?
No, it's not like that. You see, I mean, why a particular structure is stable at a particular temperature is obviously because of lowering of energy. There's no doubt. Okay? See, everything is essentially because of lowering of energy. A particular structure is formed because the energy is lowered in that particular state. So about that particular thing, there is no problem. But what I am trying to say, I'm not sure whether we are talking the same language. If you are quenching, that at that particular temperature, the stable structure could be somewhat different. I mean, the distribution of ions could be somewhat different, and when I am cooling, it could get frozen in. That is possible, and that we have also seen. This is one thing. But if you are saying that, you know, the occupancy of the A site, okay, get distorted from diamond structure, that you will be able to see in X-ray. Because then the symmetry is lost.
Right.
Then some of the peaks that your standard peaks that you are getting will get distorted. So that's what I was telling in answer to his question, that at least in my experience, I have not seen in spinel structure, perovskite may be different. In spinel structures, I have not seen that by quenching or you have found the crystal structure to become totally different from spinel structure. Spinel is generally considered as a more stable structure in that sense. So I mean, at least I have not seen the evidence. You know, maybe somebody can show the one paper where, you know, they have found something. There have been distortion of symmetries. For example, Fe3O4 magnetite is known to go to a monoclinic structure. I think it's monoclinic, right? I'm not very sure. When you cool it, okay. Copper ferrite is supposed to show a tetragonal structure, okay. And we have been able to freeze in cubic structure by doing exactly the same thing. So there are some modifications which are possible, but the structures are known to be stable in some other form. So to answer the question, maybe what you are saying is correct in certain sense, but in that case, that particular structure has also to be known to be existing. It doesn't happen suddenly randomly. I mean, the way I am presenting, it may look that in after all filling this side, why to this? Why not I put this ion here? It doesn't happen that easy.
Question. I mean, you won't get a detailed explanation of complex structures easily. So take use of the expertise of Professor Shiva Prasad.
Comparatively, garnet is still more stable.
So if we dope big atomic radius elements in that one, so obviously it will break the symmetry and the ions will sit in the site. So then the distortion will be happen, right?
No, see, the thing is that if you are changing your ions, okay, what I mean to say by stable, it means that even if you can make ion size reasonably, there is a standard ionic radii which I have given you, but I have even given you the standard lattice constant, and I have told you that normal, I mean that is 7.9 angstrom. Okay, now 7.9 angstrom you don't see in any spinel. Most of the magnetic spinels are of the order of 8.5 angstrom.
Okay.
Okay, it means already your lattice is expanded, and why lattice is expanded is because of accommodation of bigger ions, okay, which are not fitting into that particular thing, but still they have maintained cubic symmetry.
Yeah.
All right. So that's what I meant by being a structure being stable. Okay, the structure has not broken apart into a different structure altogether. though there are evidence, for example, I gave you two examples of Fe3O4, which at low temperature becomes a non-cubic structure, and a copper ferrite, which is actually at room temperature is supposed to be tetragonal, and high temperature, or maybe other way, high temperature, a different structure, a cubic and a tetragonal, and when you cool it, then you can retain that high temperature structure even at room temperature. Okay, so it's possible, but generally not very commonly seen. While in perovskite, you have a range of structures and you see varieties of structures in perovskites. In that sense, I meant that, it can accommodate a larger number of things unless the structure completely falls apart and becomes totally different. I'm sure there are complex structure of oxides. And then it can have some very defective structure of some other things.
Okay, let me ask a question. Well, you touched upon it, but maybe you could also say a few words about just like you can have a ferromagnetic transition from paramagnetic to ferro or antiferro, you can also have structural phase transitions, right? Where a particular structure is quite happy, you cool it, very often it's first order. Can you comment on that?
Yeah, that's what I was telling, that Fe3O4 is one of the example where, when you cool it down, there is a phase transition and becomes, I don't remember, it's a monoclinic. Prabhu, do you remember what happens to Fe3O4? So it changes the structure into a totally different structure, which is a non-cubic structure. So there have been cases, but not so common, what I would say. But I think in perovskite, probably they are more common. That's what I personally feel.
They are common in martensitic steels.
Yeah. Steel, yeah, that's right.
Okay, if there's no other question, thank you.
I have a few more slides which I'll probably cover in the next lecture.
Well, you can continue if you want. A few 5 minutes.
I just wanted to show them
5 minutes. Why don't you complete the
I'll
argument?
complete this particular thing. At least let me complete. If you have another question next time, you can ask me. 5 minutes more. Okay. So I have looked at only the occupancy of tetrahedral site. Let's look at the octahedral site. 16 out of 32 are filled. All right. So they always choose the alternate. So if one is filled, another one will not be filled. Next one will be filled, another one will not be filled. There are 8 B sites in P and Q. Out of these, 4 are occupied. The sites that are occupied are alternate to each other. You see, in between, these are the oxygen ions, these are the sites. These are all red one, I have put octahedral sites, which are 8. All right. Now I look at the relationship between them. How tetrahedral and octahedral are they related? If there is a tetrahedral site which is occupied, the corners of that, there will not be any octahedral sites filled. For example, look at this particular thing. This particular field is filled. This particular tetrahedral site is filled here. Now, here you have one octahedral site, another octahedral site, another octahedral site, another octahedral site, another octahedral site. None of this will be filled. So, if a particular site has taken an A ion, then in the corners there will not be any B ion. Now, this is sufficient to prove your structure. This is what I have done. All right. Now, okay, and you can map the complete unit cell. This is what I have done here. Okay. Here they are alternately, you can solve the complete structure. Now, I look, this is the last point which I wanted to cover, is the super exchange. I think you have done super exchange earlier. It's an exchange which is mediated by oxygen ions. How strong is the exchange depends on 2 factors. What is the distance between ions and the oxygen ion, number 1, and the angle between bonds. If the angle is closer to 180 degrees, then it's maximum. Shorter they are, it's maximum. Now here there are three types of exchange interaction, super exchange interaction is possible. AOB, AOA, BOB. Alright? These are the magnetic ions. Oxygen is not a magnetic ion. Okay? Three types of exchange interactions are possible. The O and B ions form, okay, let's not look into this. Let's look at this particular pair. This is B side, this is A side, this is O. Actually, I have given a tutorial problem to calculate these angles. Not very difficult. Using vectors, you can calculate very easily if you have understood this. This angle does not look that angle, but remember that's away. That's other side. This angle turns out to 125 degrees. Okay, angle between BO and AO bonds is 125 degrees. The strongest exchange interaction. See, BB exchange degree. This is very easy to see 90 degrees. It's a weak interaction. The angle is 90 degrees, so BOB interaction is going to be weaker interaction. Okay? That is AOA, which is the weakest. AO and this A. Even the distance is under root 11 A by 8. Angle is 80 degrees, still smaller. This is the weakest interaction. Therefore, spinel AOB interaction dominates, which is the antiferromagnetic interaction, which makes the material very magnetic. And this dominates so that in spite of antiferromagnetic interaction between BB and AA, they tend to become ferromagnetic and become together and interact antiferromagnetically between them. This is what is Neil's two-lattice model, about which I will talk later. I think, and at this particular point, I think it's a heavy lecture. Excuse me for that. But any last questions? You are free to ask these questions even in the next class.
Yeah. Okay. So let's close this session, and tomorrow at 9:30.